and take a look here at piecewise linear functions is what you've seen before. Now we're going to take a look at, more specific. A lot of times a function is only good for certain places, okay? From one point on x to another point on the x, okay? And then things change. If you think about the way they used to do long distance billing, even cell phone billing, you got so many so much per minute, up to so many minutes, and then after that it was more expensive. They do the same thing kind of now with your data. Cable company or internet companies are looking at that's kind of like the throttling idea that, hey, you only get so much data, and then after that it's going to either drop off and you're going to get less data, or you end up paying more money for it. So one of the graphs that we've taken a look at in the past, square root of x. We know what its domain is. We know what its range is going to be. We know that we can only put in non-negative numbers, correct? And we only get out non-negative values. So, gives us some original properties on this. So we get this one here, the x-intercept. Okay, so the x-intercept of the graph is always going to be 0. Y-intercept is also going to be at 0. The function is neither odd nor even. Okay. Function's increasing on the interval from 0 to infinity. Function has an absolute minimum of this. Thing is, I'd put in bracket, not a parenthesis there. So let's see. What about the cube root function? What is it going to do? Well, if I deal with the cube root, bring that up. Y is equal to, and I think if I have the math, yep, 4 with an x, and I just graph. Okay. So, is it odd or even? Well, it looks like it's going through the origin, correct? Well, that's not the only test that we'd have to do. I could do the rotation on there, and it appears to be, but my real test would be if I do a trace and I put in, say, 8, and I get out 2. If I put in negative 8, I should get out what? Negative 2. So if I put in negative 8, and I get that out, and I get negative 2, and I get that. So, do I have an odd function here? Okay. Does it have any intercepts? Yes, it does. 0, 0. Okay. And we can graph it. We've got it there. Now, a lot of times we will go to the graph and take a look at what it's going on with it, if that is easy to do. There are times when the graph is just simply not going to work, and we'd have to go through and do the algebraic tests for it. Okay. So, back here. Let's see here. Let's keep going, keep going. So, talks about the properties of that. Increasing on the interval from negative pi, or negative infinity to positive infinity. Okay. Local max and min. Does it have any? No, because when you take a look at the graph that we see on here, yeah, we got a bit of a kink in here, but everything is always larger the further you go to the left. You never see it really decrease. So, absolute value function. Well, we've seen those before. We get a graph that looks pretty much like this. So, is it odd? Is it even? No. Yeah. Domain is a set of all, and the range is that, so it appears to be symmetric with the y-axis, so it's going to be even. We plug in 0, we get out 0, so 0, 0 is possible. So because 0, 0 is possible, we can go on. Do we have to have 0, 0, by the way, for it to be an even function? Odd, yes. Even, no. Okay? Okay, if it was symmetric, if I seen this going up this way and I seen another one going down this way, would I even have a function? Yeah, I wouldn't even have a function with it, so there you go. Does this have a max or a min? And in this case, yes, it does. It has an absolute minimum here at 0, 0. So those are all the interesting bits about it. We know it goes through the origin. We know it has a minimum. We know it reflects across the y-axis. So, constant function. And you're kind of going, well, isn't that just a plain old number? Yeah. But is it possible to have something that is constant? Yeah. So we have to be able to identify it. What is it going to look like? Just y is equal to whatever the number, f of x, equal to whatever number it is. Now my question is here, if I've got f of x is equal to b, is x going to have any effect on b? But remember, x is putting something in. Okay, try this. That way you can get the visual on it. Okay, so say I put in 5, okay, and I hit graph. Does x have any effect on what happens to the y? No, it's not going to change it. It doesn't multiply by it, add or subtract anything to it. If we take a look at the other ones that we had over here, where we had absolute value, does this have an opportunity to change the output? Is it dependent upon what goes in? Yes. Is the constant function dependent upon what goes in? No. It's just going to be there. Okay. So, identity function. I put in x, I get out x, right? Okay. Turns out to be a line, looks like that. Square functions. Okay, something squared. Okay, cube function. We talked about these last year in terms of, say, a parent function, what the original function was, what does it look like? So, square root function always looks like this. Cube root function always will look like that. Reciprocal function always looks like this. Well, why? True, it just does, but why does it do the things that it does? First question that I'm going to ask you is, does it have an intercept on either the x or the y-axis? No. In order for it to be an intercept on the x-axis, it has to go from a negative to a positive or a positive to a negative. If I look at this function, is there any way to make a sign change in this thing? No. What is going to be a point of discontinuity in this thing? 0. We can't have x being 0 because that just simply doesn't work. So, that's why it looks like the way it does. Okay. You put in a negative, you get out a negative. You put in a positive, you get out a positive. You put in 0, you get out nothing because it's undefined at that particular point. Absolute value function. Okay. Take a look at that. Well, because f of x is more descriptive of what's going on with this. This is called Euler's notation. Okay? With Euler's notation, we have the ability to identify different functions. If I had y is equal to the absolute value of x and y is equal to 6, and I want you to add those two functions together, we've got a problem here because I don't know what's what. Okay? So we're able to label them with that. Greatest integer function. We talked about this a little bit last year. This one can get a little bit on the tricky side because we're always thinking about a number goes in and a number comes back out. You got to kind of think about this in terms of quantities in a rounding situation. Okay, if you got a 78 passenger bus, how many buses do I need for 50 students? 60 students? 70 students? 10 students? Okay, if it's a 78 passenger bus, okay, how many buses do I need if I have one student? I could cancel, but that would be, but it has to be. If I have a 78 passenger bus and I have to move that one student, I have to use that 78 passenger bus, right? But that's not the point. If all I can use is the bus, that's my function. My input is the one student. I have to use one for that. I get to use that one bus all the way up to how many students? 78. Once I hit 79 students, how many buses do I need? 2. Okay? That's what's going on here with this greatest integer function. What they're looking for is, what is the largest integer that exists? Okay? So if I start here at negative x, or negative 1 I should say, I put in negative 1, it's an integer. What do I get out? If I put in negative 1 to whatever this function is, and it's just going to be the integer, what do I get out? Okay. This is where it kind of gets a little on the weird side. If I put in negative 0.5, what will I get back out? Now, it says the greatest integer less than or equal to. In some cases, you'll hear this identified as the least greatest integer. Or another way to think about it, what is the biggest integer that is contained within? Okay. So, it's always look to the left. So if I put in negative 0.5, what's the biggest integer I get? Correct. Okay. If I look at this here, if I put in negative 1, look at the graph. And then if I put in 0.5, what do I get? I still am at negative 1. Yeah, it is a little hard to see the lines. But I get the integer of negative 1 from any number from negative 1 up to 0. Once I hit 0, do I have a new integer? Yeah, because I can bounce up to the next one. And I have 0 as my integer all the way up to 1. But when I get to 1, it jumps up to the... It doesn't include 1, because once I get to 1, I get a brand new integer. Okay? So, because if I ask what is the greatest integer between 0 and 1, I get 1, it pushes it up. But if I go start at 0 and I go up to 1 but not include 1, what's the greatest integer? Then it's 0. It's that whole bus idea. Okay? So, calculators sometimes put this out and it'll look like this, a step function. Okay? This is not accurate because it is not going to be continuous on the y. It's continuous on the x because, remember we talked about this, if I was standing down here and looking up, would I see any gaps? No, I would see it solid all the way across. But if I'm standing up on the y-axis and I'm looking, then I'll see holes in it, right? Because there's going to be steps. There's not going to be a line going from here to here. So, when we are graphing a piecewise defined function, we are going to get specific places where we use that specific function. So, if I am going to graph out anything that is less than or equal to 0, I use this. If I use values that are larger than x, I use this. Okay. Another one here. If I am going to graph this function, okay, f of x is equal to this. This is what's going to happen. If my values for x are between negative 3 and 1, I get to use this. If it's equal to 1, I get to use this. If it is bigger than 1, I have to use this. Now, where is the starting point for this thing going to be? If I am going to start this function off, we start at -3. We always identify the lowest value in the domain and we work ourselves left to right, correct? So, I can't go back to -infinity, so I know it's not going to be coming up that far. It starts at -3, okay? So, that's why we got to pay very much attention to our domain. Our domain dictates which one of these that we use. Okay? So if I want f of -2, well, I put -2 in here and I end up with -3. Okay? Correction, not -3, I'm sorry. That was my bad. 5.
Yeah.
Yeah. It's one of those days. Yeah. Last I checked, that is true. If I put in 1, what will I get back out? If I put in f of 1, I get 2. If I put 2 in there, I am going to get 4. Okay? So we end up getting a graph that looks like this. Okay? Comes out. Then, once I get something above 1, it ends up jumping up here for this point, and then once I get above that, it jumps down here. So it does look awfully strange. But when you're graphing this stuff out, if you understand what type of graph that you have, okay, what type of a graph is -2x plus 1? A line. So I'm going to have a line that goes from my input at -3 up to 1. This is a closed circle. This is an open circle. That's because,
Sorry.
got it? Okay, it's okay. That little line underneath it means it's filled in. So, when I get to this, it has to be here. But if I put 1 in here, do I really need to know the value that this is going to be at 1? And the answer is yes, I do. Because when we're going up to 1, we are going up to but not including 1. You know, it's like that whole idea, I'm not touching you, I'm not touching you. But if I am not touching you and I'm starting here, I'm not touching you, I'm way over here, right? If I want not touching you, I'm 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 not touching you. I have to get closer to you, don't I? So I have to approach you, but not touch you, okay? Same idea up over here. If I've got that, I'm going toward, you knew that was coming, didn't you? I was going towards 1, but was I actually going to touch 1? No. So when I'm looking at the graph that's down here for this, that's why you see this line going down here all the way to where this would be at, but it's an open circle. Okay? So when we're dealing with this stuff, we have to put in the 1 to this function to identify where it is going towards, but we identify that as an open circle. We have to identify the endpoint, but the endpoint is identified with an open circle because we're going close, but not quite. Because once we do that, that's when we hit the 2, and the same thing here with this. That's why when we put in the square root of this, we need to have the square root, or 1 squared. 1 squared is 1, so that's why it goes back down here, because we can think of 1.0000000000001. Okay, fine, 6, whatever. But that's what you got to do. So make sure that you go up to and include the endpoints and determine whether or not it's open circle or closed circle.